Python is interpreted, human-readable, and highly dynamic, but Silicon, the physical hardware processing billions of matrix multiplications, demands static, rigidly compiled instructions. Researchers require eager execution to build dynamic control flows, inspect intermediate values, and debug models line by line. They need to write code at the speed of thought. But GPUs are designed for massive, predictable throughput. They starve if they have to wait for an interpreter to feed them operations one by one. To hit peak utilization, they require highly optimized, statically compiled kernels. PyTorch resolves this tension through a layered architecture. It separates the high-level control plane, where researchers write Python, from the low-level data plane, where the actual computation happens.
We are going to trace this lifecycle, moving from low-level memory allocation in C++ up through the dynamic routing of the dispatcher, into the AutoGrad engine, and finally to the PyTorch 2 compilation stack. Understanding this execution stack is the threshold that separates a basic model user from an AI systems engineer capable of deploying and optimizing models at scale. When you instantiate a tensor in Python, you are creating a high-level handle that points into a deeper C++ backend. The true bedrock of PyTorch data is the c10.tensor_invol C++ structure. This contains the tensor's metadata, its sizes, its strides, a dispatch key set, and a pointer to the storage buffer. That storage buffer represents the actual continuous block of physical memory. Because the metadata is separated from the data, multiple different tensor views can point to the exact same physical memory footprint without copying it. Sitting directly above the C10 memory layer is ATen, the abstract tensor library. ATen provides the C++ tensor handles and hundreds of mathematical operator signatures, like matmols, convolutions, and additions. ATen defines the math you want to perform. It does not dictate how that math is executed on a specific piece of hardware. Decoupling the mathematical definition in ATen from the physical memory representation in C10 is a design choice that prevents hardware vendor lock-in. This allows new accelerators to plug into the framework without changing the model logic. If ATen defines the math but not the execution, how does the framework know whether to run a C++ kernel on the CPU or a Triton kernel on the GPU? The answer lies in that dispatch key set we saw inside the tensor impl. Every tensor carries a signature indicating where its data lives and what backend implementations it supports. When an operation is called, it hits the PyTorch dispatcher. The dispatcher acts as the central traffic controller, scanning an internal dispatch table to determine the correct execution path. The dispatcher extracts the dispatch key set from all input tensors. Once it identifies a match, like a CUDA key, it routes the operation payload directly down to the optimized hardware kernel designed for that device. Because this routing happens on every single operation, it is a high-performance bottleneck. The dispatcher utilizes inline dispatch tables and caching to minimize latency overhead, ensuring that routing doesn't slow down training throughput. This dynamic multi-dispatch system is the reason engineers can port models across diverse hardware ecosystems without rewriting their code. To train models, PyTorch must compute gradients. Early frameworks relied on static, tape-based automatic differentiation, forcing developers to define and compile an entire computation graph before any data could move. PyTorch uses a define-by-run paradigm. As you execute the forward pass, the AutoGrad engine dynamically spawns operation nodes and connects them via edges, building a complete directed acyclic graph ending at a final loss node. Every node records its mathematical operation using a gradFun attribute. We can trace these connections backward to the leaf tensors, the initial inputs created with requires grad set to true. When you trigger .backward, the engine reverses course. It traverses the graph via next functions edges, applying the chain rule at each node to calculate gradients from the output back to the input. These gradients are mathematically accumulated and stored directly inside the leaf tensors, where the optimizer can access them to update model weights. Storing every intermediate value during the forward pass is memory-intensive. To scale up, engineers use gradient checkpointing, a trade-off where specific intermediates are discarded to save RAM, then recomputed on the fly during the backward pass. Because this graph is built during execution, PyTorch natively supports standard Python features like while loops and conditionals. The AutoGrad engine simply differentiates whatever path the data took during that specific pass. Eager execution and dynamic graph building provide flexibility, but they are limited by the CPython interpreter. The interpreter often cannot feed instructions to the GPU fast enough to maintain peak utilization. The PyTorch 2 stack introduces a just-in-time compilation approach to bypass this bottleneck without losing the Python user experience. It starts with Torch Dynamo. Using PEP 523, Dynamo hooks into CPython's frame evaluation to observe code execution. It captures the raw Python bytecode exactly as it attempts to run. Dynamo traces the bytecode and extracts a functional intermediate representation called an FX graph. This graph is a normalized list of nodes representing inputs, operations, and return values. This FX graph is handed to Torch Inductor, the compiler backend. Inductor performs operation fusion and memory planning, lowering the graph into highly optimized hardware-specific code like Triton for GPUs. This compilation stack effectively grants developers the intuitive experience of eager Python with the execution speed of raw C++. This is the lifecycle of a modern AI operation. Python bytecode is extracted by Dynamo into an FX graph, routed by the dispatcher, tracked by AutoBrad, and lowered by Inductor into memory-managed hardware kernels. Because these primitives are mathematically abstract and decoupled from specific hardware, they enable massive distributed infrastructure. Systems like fully sharded data parallel use D-tensor abstractions to shard model parameters across a device mesh. This architecture maintains the researcher's logical model while distributing the physical memory across a cluster. As we move toward agentic reinforcement learning, these same structures support asynchronous actor meshes. Libraries like TorchForge leverage this architecture to decouple high-latency text generation from continuous weight training. By establishing a common language between researcher logic and various hardware backends, this architecture now supports the systems that power ChatGPT and the neural networks running on Tesla's autopilot. PyTorch has become the standard platform where frontier research meets physical performance.